there's also other black holes that aren't necessarily in the center of galaxies?
Very bigger than the Sun, more massive than the Sun.
NASA's legendary spacecraft Voyager 1 may have just made one of the most significant discoveries in astrophysics history. For years, scientists have speculated about the elusive dark matter that makes up a whopping 85% of the universe's matter, and some have even suggested that it could consist of countless black holes left over from the Big Bang. But now, rumours are circulating that Voyager 1 has detected a black hole, which could single-handedly dispel the long-standing theory. Is this groundbreaking news true, or just an unfounded rumour? Stick around as we explore the latest from the edge of our solar system and uncover the truth about Voyager 1's latest discovery. Black holes are a mysterious and fascinating phenomena in the universe, where massive amounts of mass are packed into small spaces, resulting in an incredibly powerful gravitational pull that not even light can escape. These enigmatic entities are formed through the collision of massive stars or by other unknown means, and according to the theory of general relativity, they can deform space-time to create black holes. Once an object passes through the event horizon, there's no way out, and while it greatly affects the object's fate and circumstances, general relativity states that there are no locally detectable features. Black holes behave similarly to an ideal black body, as they do not reflect light. Jean-Michel and Pierre's Simon Laplace first considered objects with gravitational fields too strong for light to escape in the 18th century, while Karl Schwarzschild discovered the first modern solution to general relativity that characterizes black holes in 1916. Finally, David Finkelstein's 1958 publication was the first to define a black hole as a region of space from which nothing can escape, solidifying our understanding of these mysterious objects. As massive stars reach the end of their lives, they go through a catastrophic collapse, resulting in the formation of black holes. These black holes can then grow by consuming other stars and merging with other black holes in their surroundings. In some cases, supermassive black holes of millions of solar masses can form, and most galaxies are thought to have one in their centers. A black hole's presence can be detected by observing its interactions with other matter and electromagnetic radiation, such as visible light. When matter falls into a black hole, it can form an external accretion disk that is heated by friction, giving rise to some of the brightest objects in the universe known as quasars. As stars come too close to a supermassive black hole, they get stretched into bright streamers before being devoured by the black hole. However, for decades, astrophysicists have thought some sort of unseen matter provides the gravity needed to hold galaxies like our Milky Way together. For nearly as long, some scientists have speculated that dark matter might consist of black holes, knots of ultra-intense gravitational fields typically created when massive stars collapse under their own weight to infinitesimal points. I never thought that we'd be able to contribute in any way to studying dark matter, says Alan Cummings, a space scientist at the California Institute of Technology in Pasadena who has worked on Voyager 1 since 1973 and who was not involved in the analysis. However, making black holes work as dark matter is tricky. Dark matter outnumbers ordinary matter 6 to 1 in the universe, and there can't have been enough collapsing stars to produce such a lopsided ratio. As a result, black holes would have had to form in a different way, by collapsing tiny fluctuations in the superfundamental particles that filled the newborn universe long before stars formed. Such primordial black holes could be of any mass, but they cannot be too numerous without interfering with astronomical observations. For example, swarms of black holes many times the mass of the Sun would rip galaxies apart like cannonballs crashing through chandeliers. Through gravitational lensing, swarms of smaller black holes could distort images of more distant stars and galaxies. According to Bernard Carr, a cosmologist at Queen Mary University of London who has worked on the idea for 40 years, such observations leave only 3 possible mass ranges for primordial black holes. They could have masses ranging from 1 to 10 times that of the Sun, a billionth of the Sun, or less than a quadrillionth of the Sun, 10 billion metric tons. The smallest black holes would be no bigger than an atomic nucleus. However, if they exist, the tiny black holes should emit radiation that Voyager 1 should detect, argues Mathieu Boudard and Marco Sorelli of Sorbonne University in Paris in a paper published in Physical Review Letters. Black holes get their name from the fact that anything that gets too close to them, even light, cannot escape. However, the late Stephen Hawking reasoned in 1973 that black holes should emit some light and particles. So, has the Voyager 1 really detected a black hole? According to two theoretical physicists, Voyager 1 has yet to detect any signs of such tiny black holes. However, they say the possibility should not be ruled out because Voyager 1 is still sending back data and will continue to do so until the year 2030. Furthermore, quantum mechanics suggests that empty space is not truly empty and is instead filled with particle-antiparticle pairs that briefly pop in and out of existence. Stephen Hawking postulated that when one of these pairs appears at the right distance from a black hole, one particle could fall into the black hole while the other escapes in what we now call Hawking radiation. The amount of radiation emitted increases with the black hole's temperature, which is higher for smaller black holes. Tiny black holes weighing tens of billions of tons should be hot enough to emit electrons and positrons. Earth-based detectors would miss those low-energy particles because they would be deflected by the Sun's magnetic field. However, from its position outside the Sun's magnetic bubble, the heliosphere, Voyager 1 should be able to detect them. In fact, Voyager 1 has measured a small, consistent flux of positrons and electrons since it exited the heliosphere in 2012. Even if they all come from tiny black holes, Boudard and Cirelli calculate that there aren't enough black holes to account for more than 1% of the Milky Way's dark matter. According to Cummings, the energy spectrum of the particles indicates that they are all from more mundane sources, such as supernova remnants. Carr says the new work comes close to ruling out the lowest mass primordial black holes as dark matter, but he has always preferred the scenario in which the black holes weigh several solar masses. This low mass window has never been my favorite, he says. It doesn't personally bother me if the constraints now rule it out. Voyager 1 is unable to search for higher mass primordial black holes. They would be so heavy and cold that they would be incapable of emitting massive particles like electrons and positrons. Instead, they would only emit a weak and likely undetectable light. So for the moment, the idea of black hole dark matter lives on. Stephen Hawking was a pioneer in this field, and his groundbreaking work on black holes, including his popular science books like A Brief History of Time, helped to make complex scientific concepts more accessible to the masses. Hawking's unwavering determination to push the boundaries of our understanding and his remarkable contributions to science will undoubtedly inspire future generations of scientists. One of Hawking's most significant contributions to our understanding of black holes was his discovery of Hawking radiation. Contrary to popular belief that black holes are entirely black, they emit radiation, according to his theory. The radiation occurs when pairs of particles form near the black hole's event horizon. While one particle falls into the black hole, the other escapes into space, carrying energy and causing the black hole to lose mass over time. This revolutionary idea challenged the previously held notion that nothing, including radiation, could escape a black hole. Hawking's theory suggested that black holes aren't eternal and will eventually evaporate, emitting a burst of radiation as they do so, known as Hawking radiation. This discovery has had a profound impact on our understanding of the universe. Another significant discovery made by Hawking was the black hole information paradox. According to classical physics, information about an object should be conserved. When an object falls into a black hole, it appears to vanish completely from the universe. This raises the question of whether the object's information is forever lost, thus violating the information conservation principle. While Hawking proposed a solution to this paradox, he proposed that black holes do not destroy information but rather store it as holograms on their surfaces. Information about an object that falls into a black hole, according to this theory, is preserved in a two-dimensional format, similar to a hologram. This concept is still being researched and debated, but it has the potential to solve the black hole information paradox. This idea sparked further research into the event horizon, including the idea of a firewall, which is a hypothetical layer of high-energy particles that could exist at the event horizon. The presence of a firewall implies that anything falling into a black hole would quickly be destroyed, which contradicts general relativity rules. The event horizon is the point beyond which no light may escape from a black hole. Hawking's study on the event horizon of a black hole gave rise to the concept of virtual particles. These are particle-antiparticle pairings that only exist for a short time before annihilating each other. If they are generated near the event horizon of a black hole, one particle may be sucked into the black hole while the other escapes, resulting in the aforementioned Hawking radiation. And it is for this reason that one of Hawking's final writings discloses something completely unexpected in scientific circles. Black holes do not exist, at least not in the way we know them. Although some theories on black holes have not been tested or confirmed due to a lack of equipment, the James Webb Space Telescope is changing that. This incredible instrument is helping scientists explore the mind of the late Hawking and finally confirm his theory about black holes. The JWST is a testament to what humans can achieve when they work together towards a common goal. It's a one-of-a-kind space telescope that's worth its hefty price tag and risks. Developed by NASA in collaboration with the European and Canadian space agencies with input from over 300 universities, it's the most powerful telescope ever built. After a successful launch, NASA announced that the JWST should exceed its minimum mission life of 10 years. Since its launch, the telescope has continued to achieve amazing feats, and now that we know that Voyager 1 can also detect tiny black holes, the race is truly on between the two titans.